Okay, thank you very much. Well, first of all, thanks to the organizers for putting together this very nice workshop. As you might have noticed, my title actually contains some reference to physics. So I believe I'm probably the only physicist here, or at least I think so. And I have to say that so far I enjoyed it very much. I very much enjoyed all the nice discussions. And I like to thank the organizers for inviting me to present this work here. And it will be based on a number of works which I have performed in the last couple of years in collaboration with a number of collaborators. And I highlighted here in color my junior collaborators, my former PhD student, Damian, who's now a postdoc in Harvard, Arno Hufnagel, and Jeroen Monet and Giovanni Ravazzini. Arno is current PhD student, and Jeroen left also Utrecht, and Mick is also my current PhD student. So I should give them a lot of credit for what you are going to see in the next few minutes. And I will also present some work done in collaborations with these three mathematicians. I will just mention it in passing such that you can see that there are actually kind of some useful applications coming out from this way of thinking about tame geometry. Okay, I will start with the introduction. I begin with a claim. Maybe you can say this is a sort of a gut feeling, but I want to use this talk then to substantiate this, so to kind of give evidence for this claim. And this claim is that all actual physical observables can be described using functions that are defined in a sharply o-minimal structure. Okay, it's a bold statement, but let's see how far we can get with that. But there are various challenges in this talk, as you can see in the claim. Yeah? I have to explain all the words which appear in this claim, and there are some pieces which are easy in this workshop and where I spend usually a lot of time on explaining them, namely what is an o-minimal structure. Maybe because it's more recent, I should at least spend a few words on explaining what is a sharply o-minimal structure, which is something which was introduced not too long ago, and you have already seen a talk in the beginning of the week, which I unfortunately had to miss because I was teaching. So what is a sharply o-minimal structure? It essentially endows the idea of having just a finiteness property with something quantitative, namely associating numbers to these sets, okay? Or a collection of numbers, an increasing collection of numbers, namely two integers, which in the following I will call complexity for short. Okay? And F is often called the format, and D is often called the degree. Now, what is the tough thing about sharp o-minimality is that you want to somehow treat F and D very differently and keep everything polynomial in this D in this degree. Now, where does the intuition for this format and degree come from? I give a very simple motivation. Let's think for a moment about polynomials, the complexity of polynomials. In this case, the degree and format is something very easy to understand. The degree is really the degree of the polynomial, and F would just be the number of variables if I just have a single polynomial. But another way of thinking about this F and D is really to consider it as a label of the amount of information which one needs to define this polynomial. With amount of information, I really mean in this case the number of real coefficients. Of course, this follows just from a function of F and D, but it's encoded in F and D. Okay? once we have f and d, then we can use it to obtain various bounds. For example, a Bezout-type bound, just bounding the number of zeros of this of a polynomial equation. And of course, this generalizes to multiple polynomials in a well-known way. Okay? But it not only does this, it can also be used, for example, to constrain the volume of the graph of the polynomial. So imagine that you take a ball of radius r and you embed your graph of your polynomial into some higher dimensional space. Then the volume of this ball intersected with this graph will scale in a specific way, and it will be bounded by this function c, which is in this case just a number of zeros. Okay. Now, that's good. So that's a lot of information about algebraic sets, semi-algebraic sets. But the next natural thing is, well, at least if you want to use it in physics, and of course you also clearly do this generalization, is you need to have more non-trivial functions, some transcendental functions, such that the story becomes really interesting. And the most direct question is, what about the exponential function? How do I deal with the exponential function? How do I measure the information in the exponential function? Well, the exponential function is the sum of infinitely many polynomials, so that doesn't mean that it has infinite amount of information, but rather we define it using a differential equation. So then what one does instead is one records the amount of information in the differential equation. Yeah? So how many coefficients do I need to specify, real coefficients, to define the differential equation for the exponential function? So then one can generalize this quite significantly. And in fact, one can go far beyond just the exponential function to so-called Pfaffian functions. You probably have heard about this in the beginning of the workshop, but I repeat it quickly such that we are all on the same page. So for Pfaffian functions, what are they? So they are built out of sort of building block functions, which I call f1 to fr, which are a Pfaffian chain. And again, they satisfy some differential equation, where on the right-hand side of the differential equation you have polynomials. That's very important for this discussion. What is also very important, that on the right-hand side there is some sort of triangular structure. Okay? Essentially, these Pfaffian functions are, when it comes to, for example, the zeros, they are kind of behaving similar to polynomials. Namely, one can establish specific bounds. Now, what is a Pfaffian function then? It is just, again, a polynomial in our coordinates and this building block functions f1 to fr. In fact, they form an o-minimal structure, which is the Pfaffian closure of our alge. So what is the key point I want to highlight here is that Pfaffian functions are o-minimal, or are part of an o-minimal structure, and they have a notion of complexity of the type which I also mentioned for polynomials. And the way how to introduce this complexity in this case is, well, instead of just looking at the degree of the polynomial, I record the degree of all the appearing polynomials. So the polynomial p here and the polynomials defining the differential equation. Now, for the format, it's now not just the number of variables, but it also contains the number of non-trivial functions, or the number of functions in this chain. Okay. As I already mentioned, this setting is so restrictive that you can actually establish bounds on the number of zeros or the number of poles of these functions and so on. Okay? And so that's quite nice. And the other interesting part is that at least when you restrict the Pfaffian functions, you actually can show that this structure forms a sharply o-minimal structure. Okay, so it's really, in my claim, it is one example of what I mean by that physical observables should fall into the structure. Now happens something which very often happen when we physicists work with mathematics, like recent mathematical advances, is that we actually need much more than what is already established, and you will see also this in the talk. So actually what we will need in the following, we need to go beyond this restricted Pfaffian story, even for relatively simple physical systems. But it's useful to think about F and D, this complexity, in terms of the Pfaffian setting to just kind of follow the discussion. Okay, so the first challenge probably was the easy one. Second challenge, I should explain what I mean by what is an actual physical observable. Okay, that's much harder in some sense because it's much less well defined, or in some sense more complicated to explain in generality. Now you can think of simple situations like moving planets, and then you study the trajectory, and then an observable would be where is the position of the planet depending on time. That would be something where you have classical gravity and you ignore quantum effects. However, in this talk, I will talk mostly about quantum theories and initially ignore gravity. So in this quantum theory, you have to take quantum phenomena into account, and the story gets even more subtle, what is an actual physical observable. Now, I will not be able to explain this in all detail, but you have to kind of trust me that I'm kind of picking some nice example which hopefully illustrate the ideas. So the point is that the notion of observable depends on the energy scale where I'm considering something. If I have extremely high energies, I have to take quantum physics into account. And then on the considered forces, because in the second example I told you I ignored the gravitational force. Okay, so now I want to talk about on-Tame geometry in quantum field theory, and this will be the only abbreviation which I use because it's such a long word. QFT will always mean quantum field theory. Quantum field theories are some very well-developed physical theories which are used to actually match experimental observations. So observations at the LHC are described by a quantum field theory which is called the standard model of particle physics. Okay? And this is a very well developed and much studied theory. And roughly speaking, what are the natural observables in such a quantum field theory? You can imagine that you are smashing particles together with momenta p1, p2, and you're asking on the other side, there are other particles coming out with momenta p3, p4, and you're asking yourself how likely is that such a process occurs. Okay, such a quantum process occurs. And this is measured with what is called a scattering amplitude. So scattering amplitudes are complicated functions which map to the interval from 0 to 1. And they depend on the momenta of the particles, velocities which you shoot them in if you want, and the masses of the particles, and on something which I call lambda. What is lambda? Lambda is a parameter, and which is essentially the building block coupling constant, how two particles interact, roughly speaking. Okay? But for us, it will just be a real number, okay, which has some physical meaning. Now, how does one then compute this scattering amplitude? You evaluate what is called path integrals. Essentially, what you try to do is you try to sum over all possible quantum processes which can happen in this blob here. So particles can split, they join, and so on. There are infinitely many processes, and you have to sum over them with a very complicated integral. However, this integral is very hard to carry out in practice. So what one does in many applications, that if this parameter lambda, this real number, is very small, then one performs a Taylor expansion, okay? And one gets amplitudes A0, A2, A4, or A1, A2, A3. So all possible amplitudes you get in such an expansion. And these are then called Feynman amplitudes or loop amplitudes. Okay? And there is some graphic representation which kind of quantum processes contribute to such an amplitude. Okay? Now, the key point now is that what we have shown is that taking this machinery and these explicit expressions for these amplitudes with a small label L, like really the Taylor coefficients, we have shown that if you have finitely many particles and interactions between them, then these finite loop amplitudes AL are actually definable in the o-minimal structure R and X. And they are definable as functions of these masses of the particles and these momenta P of the particles. Okay? So the upshot of this is, what I want to communicate is that there are many physicists, really many physicists, studying these scattering amplitudes because they are really relevant and they have a lot of structure. They are highly complicated functions. And they are definable functions. So they are really, it's a really a nice playground to use o-minimal geometry, Tame geometry. And they are real functions, which is also very nice. So it's something where you don't use holomorphicity or something like this. Now it would be very nice if one could see the properties of a quantum field theory in the associated structures, which you get by expanding R-Alge, including these amplitudes. Now, I want to once in a while mention some interesting questions which come up with when thinking about these questions. Is one interesting question I think one can address, as I will mention in a moment, is whether can Tame geometry formalize the connection between algebraic relations among these very complicated functions and symmetries which we expect to have in such a particle physics system. Okay? The answer to this is likely yes, and this is motivated by much of the recent progress using Tame geometry in Hodge theory. Okay? So why do I say this? Is that the transcendentality versus algebraic relations is something which is studied by these axial type theorems, and they have been established for period integrals. Okay? So why is this useful? Well, that's actually the reason or the way how we argued that all of these amplitudes are Tame functions. We argued that once you start with such an amplitude, such a Feynman integral, then you can map this to a period integral. So this is not what we did, but we just used work by others, by many others, in fact. And one can associate to a given graph, to one of these scattering graphs, if you want, Feynman graphs, an auxiliary geometry. And then one can compute on this geometry a period, so really an integral over a cycle of a p-form on this space. And this period maps to this amplitude. It really gives the amplitude if you restrict it to some appropriate slice, real slice. Okay? And then what one uses is that all steps involved in this construction are definable maps. And that the period integrals are definable in some o-minimal structure, namely this R and X. Okay? So you see we are almost there of relating the amplitude literature with the period literature, and especially like with this new insights from Tame geometry, but this is something ongoing. A second question I want to pose is, because I'd mentioned this sharp o-minimality, we want to associate a complexity to the amplitude, and we want to understand, for example, how this grows with this label L. Very basic questions. Yeah? Or how does this complexity grow with the number of particles? Very basic question. Well, can one do this? I think the answer is likely yes as well. However, there I come to the point what I mentioned before, that while there are very interesting conjectures that period integrals are sharply o-minimal, this has not been proved, and also there is no proposal even how to get f and d for a period integral. Yeah. We are playing around with this with examples, so and I know also some of you are thinking about this, so this is a very exciting direction certainly for us to explore. This is actually one is much further than just this original conjecture here, because in last year, Bignamini actually made a construction of a structure which sits inside Rn(x) and has a good chance to be sharply o-minimal, namely this structure of log Noetherian functions, which is expanded by the exponential. Okay? And one can show that the periods are definable in this structure. And in fact, it was shown using this very important work on the cell decomposition, or extending this, that it's effectively o-minimal, but it's only conjecturally sharply o-minimal. So my question, what is f and d, remains. Now this I already mentioned. From our side, it would be very exciting to see how f and d changes with the properties of the quantum field theory and of the amplitudes. And then it would give us some quantitative measure of how to deal with like the number of algebraic relations, for example. Now, why am I so optimistic that this is useful? The reason why I'm so optimistic that it's useful is that we have a toy example which we were able to explore in much more detail. Okay, and I will put this on one slide quickly. Namely, there are certain scattering amplitudes which appear in cosmology, which are known to satisfy a differential equation of a certain type. It's not too old, this construction. And one can really explicitly write everything down. Okay? And what we showed is that these actually define a Pfaffian chain. So while a general scattering amplitude is very likely not Pfaffian, we believe, these are Pfaffian functions. And then we are in the Pfaffian setting, and in the Pfaffian setting, I mentioned in the very beginning, you can do everything using these older works on the subject. Even so, the sharp o-minimality of the Pfaffian structure, unrestricted, is not shown. One can still compute the complexity and has very good bounds. So these are really Pfaffian functions in this case, and you can evaluate it explicitly, forget what is written here precisely, but there are some numbers. Now, how do I put this to use? How can this be useful? Well, this notion of complexity gives you a bound on the number of poles I mentioned, or the number of zeros. And now we can do the following. I can take these numbers, plug this into the bounds, and evaluate the upper bound on the number of poles, and what you find is really, really bad. So actually, the bound is exponentially overshooting the physical expectation, crazily overshooting the physical expectations. What does this mean? That means there should be a simpler representation of the system with which the people here, who are very clever people, have not yet developed. Okay? And this is what we now found. And it reduces the bound, still not precisely to the number we expect, but it gets better. So actually, this kind of logic is a very nice way of checking whether or not one has the best or a minimal representation of the functions, which gives you the best bounds on the number of zeros, if you have another reason to believe physically that there are so and so many poles. Now, my question to you is, given a Pfaffian function, is there a systematic way to determine the minimal D and F representation? Now, over dinner and lunch, I had some interesting discussions, especially with Andre, and I was pointed to the fact that there are even simpler examples where there is a gigantic mismatch, and it's very, very hard to match, so to say, the physical expectation with the upper bounds from the Pfaffian setting. So maybe this is too much to ask. I don't know. So I replaced it with something else, which I would be also curious, because that's what I think is somehow one of the missing steps, is there should be some substructures of this Pfaffian structure where symmetries of the problem are taken into account, and there is some notion of complexity which gives you better bounds on the number of poles or zeros. At least that would be my expectation, because that's precisely physically, essentially, where this comes from. And with symmetry, I mean something very general, more in a physicsy sense, like certain relations which you would have to build into the structure. Anyway, this is an open question which I think is interesting to be addressed. Now, so far, I have only talked about these ALs, right? These were these coefficients in the Taylor series. The issue is that if you actually want to look at the full amplitude, this full amplitude or this Taylor series is actually not even convergent. Yeah, there's very old arguments by physicists like Dyson that this is not convergent in general. So I give you a toy example. This a very simple quantum field theory, which is embarrassingly simple and doesn't even deserve the name quantum field theory maybe, which is a phi to the 4 theory at a point. And it's essentially just an integral where these amplitudes are integrals of e to some function s, and then phi to the n, where phi to the n are kind of the n particles, if you want. Okay? Now, this is not a period if you evaluate this integral, and there's a simple reason, because there's an exponential inside this integral. So it is an exponential period. Okay. Now, the first question you might ask, is this a Tame function? And that's actually one of the things I had in my early discussion with Lau, where he pointed out, well, maybe it's interesting to look in the set of Pfaffian functions, and suggested how to do this. And in fact, that's what we were able to do generally for these type of integrals. And in fact, they are Pfaffian functions. They are, when you evaluate them, they are Bessel functions. And these Bessel functions, certain Bessel functions, non-oscillating Bessel functions, are Pfaffian functions in the relevant domain. And you can even evaluate their complexity, and you see how it depends on the number of particles, how it grows. You also see that the format actually doesn't increase the higher you make n, which means that there are a lot of algebraic relations among all of these integrals. So it's very nice measure actually to have. Now more recently, we did this with all sorts of other toy models, and we were able to show that not only this amplitudes here, but also many other interesting settings of this type are definable in an o-minimal structure generated by the Gevrey functions, I think. Okay, and luckily I don't have to define this because I believe, I'm not sure, but I believe it was introduced in in one of the kind of, okay. In any case, that's what we showed. And how did we show it? We actually, we did what one would do in physics. You would expand this as a Taylor series, and you just check if it grows in the right way and if it satisfies these conditions laid out in this paper. Okay. Note, we did not include the dependence on the momenta in this. So this kind of this non-analyticity, this power series behavior appeared in this constant lambda, in this real parameter lambda. So what do I have to do next? I actually have to combine both. So I have to have variables. So it's very similar to what we heard this morning. I have to have variables in which there are the good variables, these p variables where these individual coefficients are periods. And then you have other variables in which you have this power series. And I just show it here for one lambda, but in physical theories you often have multiple directions. So some multi-summable functions. Okay. So again, I asked the question, can one extend this sharp or minimal setting to these functions? That would be extremely useful for us, because then we can carry out the question about the number of algebraic relations, not just on this individual loop amplitudes, these ALs, but on the full amplitude, which would be even more exciting. Okay. Now I should make an important disclaimer. The important disclaimer is it is not expected that all amplitudes in a QFT or in any QFT are definable in an o-minimal structure. So remember, I showed this only for these ALs, not for the full amplitudes. And how can you see that? Is you can, for example, take again these toy models and you can pick some non-definable S up here. And then it's not too hard to come up with something where the answer is also not definable. Okay. I give you another example, which is even maybe more basic, but has some important clues. Namely, if my amplitude has some non-trivial symmetry. So for example, you take my amplitudes depends now on a complex parameter, two of these lambdas if you want. Tau is now a complex number, and I transform it by SL2Z in the usual way, and it's invariant, then clearly it cannot be a Tame function on the full upper half plane, right? Unless it's a constant, because it has all these images, infinitely many images. So not everything can be Tame, so something is missing. So how can my claim which I made in the very beginning be even true? Well, there are two ways to proceed. First way, maybe we have to restrict to a class of quantum field theories which we understand very well and where we actually expect things to be Tame. And that's what we conjectured in this paper from 23. And these quantum field theories are called conformal field theories. And there we would claim that, and there are many, many known conformal field theories, all the amplitudes which come out in these conformal field theories should define o-minimal structures. Okay? There's another way of proceeding, and it's actually not unrelated to the first, but to explain this would be extremely challenging. Actually, that the tameness properties are not present in all QFTs, not in all quantum field theory, but only those which can be coupled to gravity, to quantum gravity. So what I want to do in the last 15 minutes of the talk, I want to explain why there is increasing evidence that this is actually true, that if you demand that your quantum field theory can be coupled to quantum gravity, then it has better tameness properties. Okay? Now, what is a popular picture? The popular picture is like this. It's a very cartoonish thing, but okay. Imagine that this is the set of all QFTs. Then the QFTs consistent with quantum gravity are just forming some sort of subset of this. Okay, so this is a model theory conference. This is the model theory universe, and these are the models which are tame. Okay, just as an analogy, I'm not claiming that these are tame models. Okay, so this is the picture. How to make this precise? So you can imagine that this is horribly complicated to make this precise, because what is a theory of quantum gravity? Right? That even to find out this is a very, very tough and hard goal. Well, we could work with a candidate theory for quantum gravity, which is string theory, as an example. Okay? This has been developed over the last 40, 50 years. It's a very well-developed theory. It's mathematically very well developed as well. So it allows you to make like precise statements, which is very good. And we can test things there. We can also use known quantum properties of black holes and other spacetimes, but they are often, how to say, in physics terms, semi-classical. So they kind of combine our understanding of physical principles. But you can try to use them to understand which things are allowed and which things are not allowed. But you can imagine that it's very hard to prove something explicitly. So kind of the boundaries of these sets are only formulated as conjectures. Okay? Yes?
In terms of physics, if you're not in one of these things, it means it doesn't exist?
Yeah, exactly. So indeed. And that's why it also got this slightly baroque name of swampland program. So essentially, if you're not inside one of them, you're in the swamp, you're not allowed, you just, that's not, these are not physical theories. Right? So they could not be our universe. Okay. So it's formulated as conjectures, and these conjectures are tested using string theory and these known principles. So in some sense, that's a very mathematical approach. The problem is a little bit that proving these conjectures would be almost impossible unless you have a really deep understanding what quantum gravity is. But you can collect evidence that they are true, and you can also show that they are wrong. If you find a counterexample in string theory, then the conjecture is wrong. Okay. Now, what is one of the best understood conjectures? It's the conjecture that in a theory of quantum gravity, there are no global symmetries. There's a lot of evidence for this, and it goes back many years. There are black hole arguments that they should never have a global symmetry. It has been confirmed in all string theory settings. It has been proved using some dualities. Just what I want to point out, this is a conjecture. It's very hard to prove in general, but there's a lot of evidence for this. Okay? And the statement is it has to be gauged or eventually broken. Okay, I know that probably to most of you these words mean not much, so I will translate it to something which I mentioned before. Remember that I told you that if I have a function which is invariant under SL2Z, then it is clearly not tame, right, on the upper half plane. What does now gauged mean? Gauged means that all the images of the fundamental domain are actually physically equivalent. So it means that you actually, to get the correct physics, you should just restrict yourself to the fundamental domain. And in fact, on the fundamental domain, for example, the J function, as an example of this, is a definable function. Okay? So we got already a little glimpse that tameness or minimality is something useful to have in coming from a theory of quantum mechanics. Okay? Now, I should now tell you how I got into this subject, and this comes next. So this is I gave you one conjecture, which was the absence of global symmetry. Now I give you another conjecture, which is arguably one of the conjectures which kind of pushed the whole field, just started the whole field, which was given in 2005. And it's essentially a finiteness conjecture. It's a finiteness conjecture about that these QFTs, which are compatible with quantum gravity, they should be, under certain condition, finite. And these authors, they counted them, if you want, as connected components, if you want to have a picture. There are many papers on this. Okay? So it is a central part of this program. These claims originated in string theory, and they come from the fact that in string theory, you essentially have only discrete choices when you want to connect string theory to the real world, to a four-dimensional universe. So the question at the end of the day is, do I have just finitely many choices? Okay, so that motivated these conjectures. Now, what I suggested in some years ago is actually what one should do is one should replace the finiteness statements with a tameness statement, because this would be a much stronger assertion. It would even talk to the symmetries, as we discussed in the previous slide, and make this into a much more powerful statement. Okay? And so we explored this. And that's actually how this collaboration with the mathematicians came about, namely thinking about this finiteness conjecture. So within string theory, these finiteness conjectures imply that some number of theories has to be finite, and the string theory provides you a geometry to physics map, which I cannot explain in such a short time. But this geometry to physics map, this magical map, actually translates this finiteness statement about the number of theories into a Hodge theory statement, namely that the locus of integral Hodge classes, of integral classes which are self-dual under the Hodge star operation and satisfy this bound here, should be finite. So there should be finitely many solutions to this equation, even when you change the complex structure. Okay? That's a statement you can write down. You can tell this to someone working on Hodge theory, and you can ask, is this known? And the answer was no. Okay? So I talked to Christian Schnell about this, and it was right about the time where the tameness of the period map was proved. And despite trying hard, and I tried with my students very hard later on using asymptotic Hodge theory, it's extremely hard to prove this directly. However, using the definability of the period map and the finiteness of orbits of symmetry groups, one can prove that the locus of the self-dual integral classes is a definable set, and therefore it has finitely many connected components. So this is a very non-trivial finiteness theorem which generalizes the finiteness of Hodge classes. Okay? And working with these brilliant people essentially got me hooked into the Tame world. Okay. Now the next natural step is how many are there? So there are finitely many. How many can we count them? This is still open, and it's a very hard problem. It seems like that you need the complexity of the periods, but you actually need more. You need somehow a complexity of lattices, and there I'm really struggling how to implement this properly. So what did we do? We used something which our physicists provided, which physicists provided before it was even known that there are finitely many, a number. Okay, so this is magic, and the magic works like this. Let's roughly assume that these integers, integer classes are not integers, but they are sort of, you can describe them by a density function. And then try to estimate, if this is a good approximation, how many should there be if I cut out like the wild things maybe at the boundary and so on, or control them at the boundary actually. You don't have to cut them out, sorry. And this is done using what is called a flux density. I will not explain it, but what you can do is then you can reverse engineer. You can use this number and determine the format and degree if you pretend that this would be a sort of a Pfaffian setting. Okay? And so you get a conjecture of how the format and the degree should depend on the number of variables and on the number of, on this bound here, on this number L of the integral class. Okay? Maybe one day someone shows that this is true, but it's something you can obtain from this density approximation. Now, to conclude, I want to add one more, even more recent result, which means I will tell you one more conjecture and then translate it into something mathematical, which is maybe better understandable than the conjecture itself. Okay. There has been a conjecture about finiteness of quantum gravity amplitudes. Well, you now all know what amplitudes are, some complicated functions, and now these complicated functions are supposed to be finite in quantum gravity, and finite really means like they don't go to infinity in this case. Okay. And last year, this was translated into some properties of geodesic balls inside of moduli spaces. Okay. Namely, that these geodesic balls should grow maximally like a Euclidean space. So maybe you're not familiar about moduli spaces, so let's translate it purely into a statement about Riemannian manifolds. So now consider a Riemannian manifolds, and then fix a base point x0, and then we cut out everything which is further away than a geodesic distance, smallest geodesic distance d. Okay? So you get a new manifold, and the claim is of these people, and they have a physics argument to make this claim, that the volume of these of this cut-out manifold should grow smaller than d to the dimension of the manifold. Okay? And they only claim that when d is going to infinity. Well, that looks very much like one of the tameness statements which I made in the very beginning, right? But before relating it to this, let me give you examples and counterexamples. Yes?
This is moduli space of what?
Yeah, so this is a moduli space. These are the moduli spaces which appear in theories of quantum gravity. So that's why I cannot really explain what this is. But you can also think about it, moduli spaces of Calabi-Yau manifolds, and it's true there, because their volume is finite.
But the conjecture comes from physics.
Their conjecture comes from physics. And it's really a very interesting argument how they get it. Yeah. But I cannot explain this in short time. Okay, so let's assume that this conjecture is interesting. Okay, and let's try to relate it to tameness. Well, the first thing which you notice is that the upper half plane with the hyperbolic metric does not satisfy this conjecture because it grows exponentially. Okay, while the fundamental domain with the hyperbolic metric, it satisfies this conjecture because it has finite volume. Okay, now that kind of got us stuck because the upper half plane with the hyperbolic metric looks totally o-minimal as a manifold, right? It has a metric which is very easy, simple. It's a half plane. How can this be not tame? Well, in fact, if we relate it to tame geometry, we actually have to talk about the embedding of the manifold. And now let's take this space M, this Riemannian manifold, and by Nash embedding theorem, you can always embed it into Rn isometrically. Okay? And I call this embedded space M embedded. And then we require that it is o-minimal, that it's definable in an o-minimal structure. And then I can use these volume bounds which I gave in the very beginning. I gave them just for polynomials, but they are more generally true for o-minimal sets. Okay? So this implies then, you can translate this back to the manifold, it implies exactly this sort of scaling. But it also implies that the upper half plane with the hyperbolic metric has no tame embedding into any Rn, isometric. Now, maybe that's not too surprising to you. It was surprising to us. Okay. So in fact, tameness of Riemannian manifolds is weaker than o-minimality of the isometric embedding. That's maybe not too surprising in hindsight. But it implies that actually when we talk about quantum gravity moduli spaces, which I didn't define, but then we actually should think about their tame embeddings as a condition. So again, we see that one of these conjectures, which was made completely independently of any tameness, relates very naturally to these concepts. So to conclude, I'm over time. To conclude, I wanted to present you some evidence that in quantum field theory, which is a very rich subject, and also in this way of thinking about quantum gravity, there are many interesting connections between tame geometry and physics that we can kind of learn from each other a lot and inspire new ways of thinking about it. And personally, I come from the idea of this finiteness of information, so that has particularly drawn me to the sharp o-minimal setting, and I hope that we can present some more physics application in the future. Thanks a lot. Sorry for running out of time.
Are there any questions? So for questions, you need to speak to the microphone because it is recorded.
Okay, so this tameness of manifolds, this sounded a little bit like is it related to having non-negative curvature or something like that?
You mean tameness of the embedding of the manifold? So,
Yeah.
yeah. That could very well be. So that would be very nice if there is some sort of better. I asked also around about this a little bit, to have a better criterion, like to see on the manifold itself that it doesn't have a tame embedding. That would be extremely nice if we would have that, because there are also conjectures along the curvature of these spaces. So I agree with you, but it also means that an o-minimal manifold is not yet very restricted. Yeah, at least for our context. It doesn't have yet the right restriction to be relevant here fully.
So you said that in quantum gravity there are no global symmetries, and then you mentioned the J function. But which is a global symmetry?
Yeah, but I mentioned that what quantum gravity tells you is you are just allowed to put the J function on the fundamental domain.
Okay, so okay.
So that means that in physics language, that means that the symmetry is gauged. That means that all the images of the fundamental domain are physically equivalent. They are just a gauge choice, kind of a choice of putting your origin, so to say.
But there is no physical meaning that you hold all this together, all these fundamental domains together. That one is enough.
Exactly. One is enough because kind of this captures already all the physical information. All the other ones are redundant images, so to say. But indeed, yeah.
Thank you for the talk. I have a question and a comment. The question is just from total ignorance. I've heard that scattering amplitudes can be evaluated as integrals of certain forms on like certain Grassmannians called positroids or amplituohedra or something like this. So my first question is, does this kind of thing have a place in your program? And so, okay, that's the question.
Yeah, so the first, to give an answer, it probably has, because it's like, as you well know, that like in the sharp o-minimal context, you're looking for the best representation of the information. So if someone comes, a very clever physicist, like the people who invented them, what are they? They are essentially just very clever representations of the informations in these amplitudes. And if I would be able to measure their complexity in a sharp o-minimal sense, I might have a way of getting better bounds on the zeros, for example. So I think it has a place, but we did not look at this at all.
Okay, thank you. And just my remark is that on slide 3, you said, you quoted the theorem that the Pfaffian structure is sharply o-minimal. It's written Binyamini, Novikov, Zak, but this theorem is due to Binyamini and Vorobyov.
Okay.
Just a small remark.
Yeah, I was not sure about the citation, and then I just said...
It's hard, because it does not appear in the paper of Binyamini and Vorobyov, because there is no notion of sharpness, but you know,
yeah,
as
I
a theorem,
so
it's...
exactly,
yeah,
then,
okay. Thank you.
Very good. Thanks for pointing this out. Fix this one of mine.